In this module, we shall revisit logistic regression from the viewpoint of a practitioner. We have seen that logistic regression can be used for the case when we have a binary outcome and that it is a very popular model choice. Its popularity can be due to various features. One is because it turns out to be the canonical link for the binomial family, and this leads to desirable mathematical properties. This also makes it the default choice in many software packages. However, this agreement purely from the mathematical standpoint will not satisfy the practitioner, and thus we will revisit logistic regression in this module from an econometric angle. The econometric argument for logistic regression, or more generally for probit regression or any choice of link, comes from something called binary choice. The idea here is that in addition to the binary outcome and the set of covariates, for each individual there is also a latent set of covariates which determines the decision taken by the individual. That is the binary choice which leads to the binary outcome. This can be motivated based on the idea of utility. Some part of it is explained by the covariates and some of it is unexplained. This can be motivated from a very popular economic concept called utility. The idea is that some part of the utility of a decision can be explained in terms of observed covariates, while some part of it is unexplained random variation. The distribution which we attribute to this random variation is seen to influence the choice of link. We shall discuss this in more details in the remainder of this module. In this lecture, we shall consider the problem of defining regression models for the case when we have binary outcomes. We shall define the linear probability model and then the concept of binary choice. The ultimate purpose is to define a regression framework when we have observations on a single response y, and we want to explain this outcome y in terms of p explanatory variables x1, x2, xp. So for example, we might have observations on x1, x2, xp for some future observation, and we want to predict what the unknown y is based on x1, x2, xp. Or we might want to consider the x's singly or maybe even jointly, and to see how y changes as a function of these x's. So this is the typical regression problem. Here is a typical regression equation using a model data set from R. So this is a regression equation which explains the savings rate of countries using some covariates, such as the percentage of the population which is below 15, the percentage of the population which is above 75, etc. Now recall that the methodology for fitting regression models to continuous outcomes first consists of some exploratory data analysis, where, for example, we might want to plot the response against each covariate taken in turn, observe whether there appears to be any relationship at all, and if so, whether the relationship may be considered linear. And using these exploratory diagnostics, we want to frame a multiple regression model which explains y in terms of the joint behavior of x1, x2, xp. Recall also that the technique for fitting the regression line is the well-known least squares technique. So let us apply this least squares technique to a problem of determining school choice from actual study which was done in India. So here we have observations for a number of children on individual level covariates, household level covariates, and our purpose is to predict whether or not they go to a private school or to a public school. So we did it as I just said. We write out the multiple regression equation, we do some exploratory data analysis, and then we use least squares, and what we get is the line which is given in this figure. However, we have a problem. Note that what we are predicting is the percentage of children who go to private schools. And yet we see that for certain segments of the linear predictor, the predicted percentage is either exceeds 100 or is below 0. Now, why did this happen? To understand this, let us take a step back and consider all kinds of outcomes that arise typically in econometric problems or other applied problems from the viewpoint of a statistician. So on this slide, we see several types of outcomes, which have been color-coded according to type. So household income and share prices, which have been indicated in blue, are the most common types of outcomes, which are continuous variables. Family size, mortality, morbidity, fertility, which have been indicated in purple, are yet another type of variable for the statistician. They are called count variables. The remaining variables, which have been indicated in gray, are called binary variables. So statisticians record these variables using 1 or 0. The value 1 occurs if a certain event occurs, and 0 if the event does not occur. So what kind of events might we be interested in? If we, to begin with, consider econometric problems, which is historically the field from which the concept of binary choice has arisen, a very common model is the question of determining whether or not an individual migrates to a different country. There is, in fact, a very famous data set and famous application which has motivated the origin of some statistical methodology concerning whether or not an individual migrates from East Germany to West Germany. The problem thus is to measure certain individual level covariates on a group of East Germans and then using these to predict whether or not the person is likely to migrate to West Germany. Similar questions can arise. For example, if we consider what about an individual determines whether or not the person is employed. What factors about a country or its neighbors might determine whether or not there is civil war? So these are all central problems in econometrics. And in each case, we are concerned with a binary choice. That is, a choice between whether or not an event will or will not. So formally, to define binary response models, we are interested in an outcome which takes the value 1 if an event occurs and the value 0 if the event does not occur. Now, we have seen that the problem of determining school participation falls in this category. Yet, when we fit a linear regression model to this data, we got a problem, which is that the predicted probabilities often lie outside 100, outside the acceptable range of 0 to 100. Now, why does this occur? This occurs because there is a certain constraint for the binary choice, which is that the mean of the binary variable is equal to its probability of success. Now, as we have nothing in our fitting procedure when we fit a linear model which takes into account this constraint, the problem of typically getting predicted values which lie outside the acceptable range can occur. So, any acceptable methodology for this kind of data must take into account this constraint. So let us first, before exploring further the concept of binary response models, consider something called the linear probability model. The linear probability model is the simplest possible model for binary data, and it does what I have just been saying in the context of the school data, which is to fit the linear model as is in its typical specifications to the case of an outcome variable, of a binary outcome variable. So the situation is that we have a set of predictors x1, x2, xp. We have a single index x prime beta, and I'm going to assume that expectation y given x is equal to x prime beta, which is typically done in a linear model. Now note that when y is binary, it can assume values either 1 or 0, so its expected value is also equal to the probability of it assuming the value 1. So this is why when the linear model is applied to binary outcomes, we rename it as the linear probability model. So to repeat, the linear probability model states probability of y equal to 1 given x is equal to x prime beta. So revisiting again our school choice problem. To repeat, we have certain covariates for a group of school children. Now this is data from an actually published study. The covariates for an example include individual level covariates such as the Raven score, how many siblings a particular child has, and also includes household level covariates such as the household wealth. This slide shows the outcome as well. So the outcome, which has been called PUAIND, is the chance of whether or not the child goes to a private school. So to begin with, we do some exploratory data analysis on the data, and then we fit the linear probability model. So here again is the graph which I just showed you earlier, and again we note that there is a problem with this fit. The problem is that when I look at the predicted probabilities, the predicted probability is larger than 1 for 61 observations, and the predicted probability is less than 0 for 81 observations. Now, this is clearly not useful if our ultimate goal is prediction. And again, the problem arises because we have in nowhere considered the constraint that the expected value which we get from the model must lie within the range of 0 to 1, because in this case it has the additional interpretation as a probability. So shortcomings of the linear probability model. The first is, as I just said, that we can get predictions which are outside the acceptable range and hence not useful. The second is that the concept of linearity of probability is also not acceptable. Now, what do we really mean by a linear model? Now, note that when we say linear model, what we mean is linear in the parameters. So this means that it is unbounded. So by a particular choice of covariates or a particular choice of parameters, we can always get probability values which either exceed 1 or are below 0. So this is why when we are modeling probabilities, the concept of linearity is not acceptable. So say we persist with the linear probability model for the school choice data. It would say, for example, that an increase in the wealth of a family by 10 units increases the chances of a child going to a private school. However, if we consider this from a subject matter point of view, an increase of 10 units from, say, 500 to 510 scaled units can be expected to be quite different from, say, 10,000 to 10,010. So this means that the idea of linear is not necessarily acceptable for all applications. So this is the second shortcoming of the linear probability model. The third shortcoming of the linear probability model is a more technical one, which is that the residual is heteroskedastic by definition. Now note that an alternative way to write the linear model is to write y equal to x prime beta plus e. The typical linear model assumes that variance of E is sigma square for all individuals. This is the assumption of homoskedasticity. It is an essential assumption because we can show that under this set, we have something called the GaussMarkov setup, and it is possible to show that the least squares estimator of beta is in some sense the best possible estimator of beta. However, when the assumption of homoskedasticity is violated, then the linear model is firstly not necessarily the most appropriate technique for the data, and secondly, the resulting OLS estimators, as we call them, the ordinary least squares estimators, are not necessarily best. They are not invalid in the sense that they are still unbiased, but they are not the best in the sense of having minimum variance. Binary data typically leads to heteroskedastic errors. The reason is that each y conditional on x may now be considered to have a Bernoulli distribution. The mean of the Bernoulli distribution, as we specified, is the probability of y equal to 1, which is equal to x prime beta. The variance we know for a Bernoulli variable is pq, which is the probability of y equal to 1 multiplied by the probability of y equal to 0, which is equal to x prime beta into 1 minus x prime beta. Thus, sigma square becomes a function of x, violating the assumption of homoskedasticity. So, to summarize what we discussed in this video, we began with the concept of defining the regression framework. We observed that there might be many kinds of variables. From the perspective of a statistician, they are classified into continuous, count, and binary variables. We started with using binary variables and considered the problem of binary choice. We then moved on to considering the consequences of what would happen if we applied the linear model as is to binary observations. The resulting model is the linear probability model, and as we noted, it is not necessarily the most suitable model because it has 3 glaring drawbacks. First, that we can get predictions outside the range. Second, that linearity is not acceptable when we are talking about probability. And thirdly, that we have heteroskedastic residuals. In our next lecture, we will consider the alternatives which have developed for the linear probability model. In this module, we have looked at the concept of binary choice. This is a popular argument used in econometrics to motivate the choice of the link function for the case when we have discrete outcomes. We have seen that binary choice can be explained in terms of the utility obtained to an individual from a particular decision, and that part of this can be explained in terms of covariance, while part of this is random variation. We can attribute a distribution to this unobserved random variation, and the choice of the distribution function will ultimately determine our choice of link. So, for example, if we assume that we have a normal distribution, it will lead to the probit link. If we assume the logistic distribution, it will lead to the logic link, and so on. Logistic and probit regression are very popular models used to model binary outcomes, and we shall see more of them in subsequent modules.